So welcome everyone. This is Engineer Mohammad Hamad, and it's my pleasure to host today's webinar on design of columns, mastering reinforced concrete and composite sections using CSiCOL program. So this webinar has been presented in the CSI Bangkok office located within AIT. As many of you know that AIT is an international postgraduate institution focusing on engineering, sustainability, and management studies. This institute not only prepares graduates for professional success, but also for the leadership roles. So here is the AIT, and CSI Bangkok is located within the AIT. CSI Bangkok vision is to bridge advancement in civil and structural engineering through knowledge, insights, and innovative software solutions. CSI Bangkok's aim is to equip engineers with cutting-edge software solutions to help advance their careers and to take part in the development of resilient and sustainable infrastructure. So CSI Bangkok is an affiliate of Computers and Structures Incorporated, commonly known as CSI, the key software development company in the field of structural and earthquake engineering since 1975. About 160 countries and thousands of engineering firms using their softwares. Recently, they have celebrated their 50th anniversary, and these events are part of that. CSI Softwares is backed by more than 4 decades of research and development, making it the trusted choice for the design professionals everywhere. They have several sophisticated engineering products like ETAPS, SAP 2000. Among them, one of them is the CSiCOL that we are going to use in this webinar. CSiCOL is a comprehensive software package for the analysis and the efficient design of column cross-sections. So in order to make this opportunity fruitful, because we have the team who developed this CSiCOL program, and these are the part of this one of the presenting team. Let me introduce our presenters. The first one is the Dr. Naveed Anwar, who is the CEO of CSI Bangkok and the adjunct faculty of a structural engineering program at AIT. He has more than 40 plus years of experience in structural engineering field. And the second presenter is Engineer Shehezard Rifthie. He's working as a software engineering manager at CSI Bangkok. So let's start with the first presentation by Dr. Naveed. In this presentation, he will present both theoretical foundations and practical consideration for the design of columns. So Dr. Naveed Anwar, thank you for joining us today. The floor is yours.
Thank you so much, Hamad. So welcome everyone. And those of you who we have met, it's good to see you again. So when we talk about any software or any technology, I think the first thing that we need to do is to look at the software under the hood, or that means how does it work. And often in the old days, when you open the hood of a car, you could see the engine, you could see all the components, and you could see how they work. But if you look at any of the modern cars these days, and you open the hood, you find another hood or a black box underneath. So which means that most of the software and most of the things these days are hidden from the people. Earlier, and because of the technology, it wasn't so advanced, so everything was exposed, was visible, people could see and interact with the things at a very low level. But now, most of the time, we are just dealing with a high-level interface, and we don't know what's going on behind that. But today, we want to go, and take a look at CSiCOL and see where it came from. So under the hood of CSiCOL is actually this book, which is called Structural Cross-Sections, Analysis and Design, written by myself and one of my students at that time, Dr. Fawad, who is now in Canada and as a faculty member. So we wrote this book at the same time that we were working on some of the development of CSiCOL. So both the programs and the book are actually interconnected. So you can find most of the theoretical background for CSiCOL and other programs in this book. Now, I want to emphasize just briefly before I hand over to Shehezard to show you how things are done, to see where these things are coming from. So if you look at CSiCOL, the output that we get, response that we get is three kinds. One is the section response related to section itself. One is related to this capacity, and one is related to its moment curvature. And you get a lot of further response from there. So I want to just share with you how these three main categories of response are computed. So first of all, the section properties, area of cross-section and all, is based on general rules of integration. I think many of you know already. So we can use these rules to integrate the area, moment of inertia, shear areas, and all of that. So that's one thing. Second one is that once you have a composite section, then we also bring in the modular ratio, because different materials have different elastic modulus. So you calculate the modular ratio and you modify that to calculate the elastic stresses. So this is the modification to the basic equation for composite section, which is also well known. This is where things get interesting, which is, I think, quite unique to the program that we're talking about. When we talk about a general cross-section, we actually define the cross-section to be of a very general form, a cross-section which is made of general zones, each zone having its own material or properties, and each material is simply defined by a stress-strain curve. So we basically, when we develop the theory, we don't think about concrete or steel or anything. This cross-section could be made from bamboo, from plastic, from anything. As long as we have the stress-strain curve, we have the configuration, we should be able to solve this cross-section. And based on that, then we develop the general representation of the equilibrium equation. I'm just going very quickly to remind you how these things work. So we have a cross-section, which is now a reinforced concrete section, a composite section, and also we put in some reinforcement, rebars, and also post-tensioning, because post-tensioning, once again, is just a material. And then based on that, if it is undergoing a certain deformation, we can write the general equilibrium equations in that way about, axial load and to any arbitrary axis. So after having those equations, which are basically integration of stresses over the area for which they are assigned, we get the total stress resultants. And then we can use this analogy that if you have a beam cross-section, and if you look at the typical way that we define the stress-strain curve on it, then we can assign the concrete curve, and we can read the concrete stress at the specified strain of 0.003. We can read the steel stress at specified strain, and then we can just add them together. And because there's no axial load, so we just get moment equilibrium, and we can calculate the moment capacity. So that's the simple application of that concept to a very simple cross section. Now, same thing can be applied to three quantities, moments, and as well as the axial load, and you get now not one, but you get three numbers, and you get this interaction between axial and flexural capacities, which is called the axial-flexural surface, interaction surface. This interaction surface we can subdivide, or we can visualize it in two ways. One is we cut it vertically. We look at PM interactions, moment versus axial load interaction, or we cut it horizontally. We look at the two moment interaction, MX and MY interaction. So we get full behavior understanding of the cross-section capacity for a given strain constraint, which is 0.003, 0.035. So this is a arbitrary surface, failure surface we generated for particular strain and stress condition. And actually, when I teach this one, I normally give the analogy of a watermelon, where you have a watermelon and you cut it vertically and horizontally, and you get those information. So students tend to remember this more clearly, how this came through. Now we will show you how this interaction surface is actually generated, and this is part of CSiCOL program. You can actually see it by yourself. You can just play this animation. It shows you for each cross section how the nuclear axis is being rotated and the nuclear axis is being changed, and the corresponding points on the interaction surface being generated until the entire surface is complete, and then we can use it for capacity calculations. So this animation is useful to understand how it works, and also is fun to watch. So that interaction surface that I showed you is theoretical. It did not include the codal provision. So we have to now bring in the codes. So in CSiCOL, we can handle that many codes, I think 14, 15 codes on the HEP. And these codes come in to specify material models, stress-strain curve, capacity factors, material factors, and slenderness and all. So we first determine the general capacity, and then we enforce the code-based constraints on top of that to get what is the code specified. So when we bring in the codes, the blue line is the theoretical curve that we computed, and the orange line is the ACI code curve version after applying all those factors that I mentioned. So that means you can see that we reduce it by certain numbers to include factor of safety and other constraints for each code. So that's the figure from ACI 31821, and that's how they interpret the interaction curve, theoretical and the applied or applicable based on, and remember, this is still based on ultimate load. The actual loads are somewhere in between. So this is still a way far from the theoretical capacity. So that's about the capacity. Moving on to the curvature. When we have a curvature in a section, obviously, then we get the stress strain curves like that. And then in this case, we equate them for a simple beam based on the code, and we can derive a simple formula, which is a simplified form of the general formula that we have used. So code equations are just very specific cases of very general case applied to rectangular section with rectangular stress block and so on. Now, if we move forward to a general curvature case, which is not with the code, and we go from 0 to maximum possible deformation, we apply load to a beam, and then beam deforms, and then we get a curvature, and then for each curvature, so then if you see that, then we have once again the steel and the concrete stress strain curve that we have used in the cross section, but this time we are not limited by the 0.003 strain value that we used for the capacity. We allow it to be free and depend on the actual curvature. So that is the case, it can come from any location. So any strain corresponding to a curvature can go back, read the stress, and get the equilibrium equation. And then based on that, we can then determine the moment for that curvature. So this way we can generate the moment curvature point for a given curvature, assumed curvature. And so to conclude, we have this one, and if you fix the strain and vary only the neutral axis depth, you get capacity curve. And if you vary strain, vary KD, and maintain load equilibrium, you get moment curvature using the same equation. So both of them are actually using the same equations, just using differently. But moment curvature gives us far more information than capacity ever can, which I discussed in another video. One more thing, the last item that I want to discuss very briefly is that this is an interaction that is not normally discussed. And this is an interaction between axial load and the curvature and the direction of curvature. And if you plot those in a surface, it will look something like that. So this is very important for columns when they are axially loaded, and we are interested to find curvature relationship with different directions. So now if I compare them side by side, the left-hand side is a curvature versus axial load plot on different section of the cross section. Right-hand side is a load and moment plot from the capacity. So two are very different, but they look similar in terms of how they behave. One is derived from moment curvature, another one is derived from capacity curve. So if you move that, and you can see, if you cut that, you get the PM interaction. And if you cut this one vertically, you get an axial load versus curvature interaction. So you can see how the curvature capacity decreases as axial load increases. And then on the right-hand side, you see the moment and moment plot interaction between them. And similarly, on the left-hand side, you see the change in the curvature capacity along the different sides of the cross-section. So that's how we can interpret the whole cross-section capacity and curvature based on the equation that I saw. And all of this that I've shown you is implemented in CSiCOL, and all of the diagrams are taken from there. So I think now it's time for us to move to the examples. So I hand it back over to Hamad.
Thank you very much, Dr. Naveed. The presentation was very insightful. So next, to link the theory with real-world application, I'm pleased to introduce our second speaker, Engineer Shehezard Rifthie. He will conduct a live demonstration of CSiCOL program, showcasing how this programs act as a powerful tool in designing the efficient cross sections. So, Engineer Shehezard Rifthie, the stage is yours.
So thank you, Dr. Naveed, as well. And now I will show about CSiCOL. So I will go through the different features of the program. First of all, as you can see, we have different templates and the ability to import from eTabs and the wizard. For this section, I will show about the wizard. In the wizard, so basically it's single form where you can go through the entire process of defining your material properties, your section, the loading, and all the way up to the report generation, which will generate a single page report. This you can do in a few minutes. So let's go through that process. In this example, we will be using the metric Unix with the ACI code. As well, there are other codes available in this program, as mentioned by Dr. Naveed. In addition to this, we have options to change the graphics and add your own rebar sets. Okay. And then in the next section, we will choose material properties. For this example, we will use grade 40 concrete and set our properties 40. And then for the rebar, we will just round off the values and keep them as they are. After this, we will select our rectangular section. So for this section, we will go with a 300 by 300 concrete section, and our car depth will be 30. For this example, we don't want to have any bars along 2 or 3 and only having the corner bars. Once this is done, you can then add your loading. For this example, we will add loading of 1000 kilonewtons and a moment of 40. After we add the loading, we can see the maximum capacity ratio is at 0.71. Then we can check the detailed results. So in this detailed results, you can have additional information on the neutral axis depth and the moment angles. Along with that, there are the different calculations which were performed to determine the maximum capacity ratio. Once this step is done, you can also view the interaction curves. So over here, we have interaction surface in 3D, which you can view. And then in the top left, top right, there is a drop down for the angle. And in the angle, you will get your load combination. So this load combination is the load combination generated at a specific angle, which is the neutral axis angle. And that will give you the combination loading, which is within the capacity as shown here. And then the final step, you can generate your report. So this report is just a single page report with the critical information for your column. Let me go back to that. As we can see here, you can note the maximum capacity ratio, the rebar ratio, and the rebar configuration, including the total area of rebar. All right. So this is our quick design wizard. Now let's move to another step and assume, let's say that we are increasing the loading for this section from 1000 to 1800. And when this loading is increased, we will have our capacity being outside of the interaction surface, as shown here in the interaction diagram. Now, in a case like this, what can be done? So let's look at that next. As you can see here, the remarks, it says it's not okay. For this step, we will use auto design. So auto design helps the engineer to optimize a section and bring it to within the limits specified by the engineer. For this example, we will go with our smallest bar being D12, largest bar being D25, and setting our maximum rebar ratio to be 8% and our DC ratio to be less than 0.9. And then we just click run. So this is our final output. And here it says that the capacity is below 0.9 and the rebar ratio is at 4.19%. So this section, let's click OK to accept this section. There is also additional tools available for the options, which are where you can follow the provided layout And when you follow the provided layout, it will take the current layout and try to find a suitable reinforcement layout for that section. But in this case, it has failed. So if we want to go further, we can add bundled bars. So when we add bundled bars, it will find another section including bundled bars. Now let's take a look at our capacities. So in here, we can see that our capacity is at within the limits of this interaction surface. It's at 0.89 as seen here. Here we can see that our moment angle and neutral axis depth have changed. All right. So in the next section, I will go over further results as mentioned by Dr. Naveed regarding the animation of the interaction surface. This tool is more of an educational purpose, and it shows the user how the interaction surface is generated. So we go angle by angle to generate each PM curve. As you can see here, starting from the pure tension point to the balance point to the pure compression point. And then in the next step, we have the capacity point details. So in the capacity point details, we can see the different points and the point status of each section, from the pure tension point to the next is the balance point, and then the pure compression point. So this one is for the load combination ones. Another tool that we can use is called the multiple curves. So with this one, let's say we want to check for our load combination one, the different concrete strengths that can be used. As we can see here, grade 20 and 30 cannot be used for this loading combination. So we can go with grade 40. Then let's look at the steel strengths and set them. So we can see from here, our steel strengths, we don't have to go as high. We can even use like say 300 or 200. Then we can also compare it with the different rebar combinations. So we will choose D14 and D18. So for D18, it's our combination and demand is within the limits of the capacity. Now we will take a look at creating a complex section. So in here, we will create a section and add our loading. So we will choose an axial load of 4,000. And just to note that this section currently has an area of 360,000 millimeters. And also you can view the section mesh. It's a simple mesh because there is no confinement. And then we view our interaction diagram for that load combination. So once we have all this, also an additional feature in here is that we can view the tables and see the different points for the point status from tension control all the way up to compression. We can easily click, copy, and paste the whole table in Microsoft Excel. So let's create a chart for this data to compare with our composite section. Once our chart is here, let's go back and see how we can modify this to become composite. So from here, we can go to the add library and add a steel shape from the AISC 14 library for an I section. So in here, let's add one I section, which will be within these limits. Let's take W360. All right. So now let's compare our section properties with that of the previous. As you can see here, the section area has increased. This is because we are using the transform section properties to calculate all of these section properties, including the section modulus. So this can also be seen and which sort of section mesh that we are passing to our solver to generate the section properties. As you can see here, the I section within that. Now, if you take a look at the interaction diagram for that load combination, we can note that the load combination is now within that capacity, since the capacity has increased for that demand. We can simply copy this information from the table and paste it again in our Excel sheet. So as we can see here, the orange line is the composite section's capacity, PM surface, and the blue line is the normal one, non-composite. The next one, in the next video, so for this demonstration, I want to show you how quickly and efficiently you can create any complex shape. So this one was done for creating an oval column for a bridge pier. So this was done in real time and it took under 2 minutes. So compared to most other software, this one is very powerful when it comes to its drawing functionality. So we can simply merge the section from the home ribbon menu. And then let's add our rebar. So we'll draw 2 circles and then align them. Once this is done, we want to get rid of this rebar in the middle. So what we can do is go to the draw menu and click explode. So this will explode and create single rebar points on our section. So let's do the same for the other and then select the ones in the middle and click delete. Then we draw a line rebar from one end to the other on the top and on the bottom as well. Now we can modify the line rebar pattern. So I want to have just 2 bars and I don't want to show any start or end bars. So I will get rid of the start and the end bars. In the next section, let's talk about how we can apply confinement to our column section. So for this example, I will use a D25 4 by 4. So this is our section. And for this section, we will have our, let's view our moment curvature diagram. So in the moment curvature diagram, we can see the different point statuses from going from normal to cracked point, and then the point where the concrete cracks, and then we find the point where it's yielding of the bars, and then finally the concrete is going to crush, and after that we have our bar failure. So by hovering over the moment curvature diagram, we can view all this information. As well, you can see it in a tabular format with the point statuses mentioned. So let's copy this and paste it in Excel. So this data we will use to compare and verify with the confined section later on. Let's go back to our section. In here as well, we have our moment curvature details. So this gives you a side-by-side comparison of the stress and how it looks at different points during the application of the loading. As you can see here, it's currently in normal state, and then the concrete cracks, and after cracking, it will go to the bar yielding point, and then it gets to the point where the concrete is crushed. And when the concrete is crushed, we will see the spalling of the cover. Then the next step is going to be complete failure. All right. So next, we want to create our confinement. So it's as simple as clicking the auto confinement in the home ribbon menu. We can see here, simply click. So what happens when we click auto confinement is that the program will create the Mander confined stress strain model, Mander rectangular confined stress strain model, and add its properties, including drawing the confinement zone. So all of this happens in a single click. Let's view our Mander rectangular and update the spacings to match with our section. So for this example, we will have confinement stirrups on every bar. So that means our spacing along X and Y is going to be 100. Next, we will copy this stress strain data into Excel to show you the difference in the Mander versus unconfined versus confined. Once this is done, we will see the section which is not in the confinement zone. So this will have a distress strain of Mander unconfined. So we'll simply copy this data into Excel, and you can see the difference between Mander and Mander unconfined and Mander confined rectangular. the difference in the strain value and the strain limits. So the maximum strain is at 50 for Manda confined compared to Manda unconfined. And we also have an increased strength in the concrete because due to the confinement. And this is what we want to achieve with our confined sections. Next step, let's view what the difference is by adding confinement with the moment curvature curve. As we can see here in this curve, it goes way past the point of an unconfined model. The concrete cracks, the first bar yields, then we have concrete crushing, but then it keeps going further. The remaining part of this curve is carried through by the confined portion of the concrete section. We'll copy these values back into Excel and compare with our unconfined section. Okay, as we can see here, this shows us that the ductility of a confined section is much higher than that of an unconfined section. So what this means is that we are able to prolong the failure of a concrete column by adding confinement. Let's view that in the moment curvature details. As we can see here, the purple zone is the one which is in the confined concrete, and the blue is the unconfined portion. So as we move through this graph, we will see the different, how it behaves at different moments and curvature, the strain values. So we see the concrete cracking, and you can notice there is a difference in the stress plots slightly between the confined and unconfined regions. So once we reach bar yielding and then the concrete is crushed. So after this point, the remaining region is carried purely by the confined concrete section, as we can see here. So this one, it goes all the way until failure. This diagram shows us that confinement can help to actually save lives in the extreme events just by prolonging its failure point. Next, we will talk about the moment curvature plot. So this one is very interesting. And how do we read this? What does it mean? So let's look into that. This is the axial versus curvature plot. So every point along this curve, so we have our curve here. Every point in this curve over here is a maximum curvature along a specific angle. Now, if we take a look at what that exactly means. So in here, we have our axial loading. When we increase our loading, the maximum curvature point will decrease. And that is what the axial curvature plot is showing us. So previously we had in a load of 400. So our maximum curvature point will be at around 0.3. But when we increase our axial load, our maximum curvature point will reduce. So this plot over here is basically showing that maximum curvature point. This chart can actually help an engineer to gauge on how much loading and ductility, and to give an idea of how much loading can be applied before it fails in order to prolong its failure point for different loading conditions. So now in the next example, we will look at the stress strain for loading. The stress strain for loading is basically showing us the different strain levels and stress levels for that specified load combination. Now, in this case, it's for a confined concrete section, and we can see the stress levels within that neutral axis depth all the way up to the blue point 2.3, and then the bar stresses in terms of its tension and compression. Then we have the concrete strains, the strain levels at different zones in the section, and then the bar strains. This can be viewed in 3D as well, which will give you an idea of how the section is going to behave for that specific loading. An additional feature in our program is that we can apply to consider concrete tension in the stress strain curve. So what this does is it gives an additional tension portion to the concrete to allow it for straining for the negative strains. So how does this affect our stress strain for loading? As we can see here now, it gives us a tension portion below the neutral axis point for the concrete to take on some tension capacity during the bending. Okay, I will hand it over back to Dr. Naveed for his comments.
Yes, yeah, thank you, Shehezard. I just wanted to, first of all, highlight some of the important things that you have shown and see how they are useful in while we are doing the column design, especially for the application of ductility and also how we can prolong the failure points as well as using composite sections. So I think many of these features are quite useful when we are doing bridge piers and also building columns which are subjected to large curvatures during earthquake simulations, as well as the real earthquake. And these moment curvature curves with confinement models can then be used as an input to the moment rotation curves, which can then be used as an input for a nonlinear analysis, for example, for pushover analysis, or even for combining it with the time history analysis in different programs. And these are based on exact solutions, because sometimes some of the programs are using the fiber mesh to simulate similar moment curvature curve by dividing the sections into rough fiber, which is good enough for if we are doing a whole building. But if we are really interested in a particular cross section or the behavior of one column, then we use exact integration as we're using in this program to calculate the moment curvature. So there'll be some difference between the fiber mesh that some programs use and the exact integration that we are using here. So I think a lot of the information that we presented here is quite helpful in evaluating the column's capacity as well as curvature. And most importantly, I think the understanding of the stress strain state for a given loading. Because as I mentioned, the capacity surface is for a particular strain value, and it is for an ultimate load, which actually never happens in the loading history of a column. But if you are interested for a particular loading, let's say at earthquake at service level or earthquake at collapse level or MCE level, then we can use those inputs and determine the cross-section stress state and strain state at that point. So I think I just wanted to add a little bit about the significance of all of these response that we have put in the program. Another thing that as Shehezard has shown you, the composite section as well as the general sections. So this can also be used for evaluating the capacities of retrofitted section, because often we have concrete of two different strengths, old concrete with a new concrete around it with different strength, or steel with different strength, or we add some angle sections or plates around the section. Then the program can be used to evaluate the capacity as well as curvature capacity of those kind of sections. So I think we can continue with one or two important examples, especially one example which is coming up, which is on the girder, because one of the things that I mentioned earlier, that the program is general enough that we can use it for even pre-stressed and post-tension sections. Because for the ultimate evaluation, post-tension section is the reinforcement, or the post-tensioning is just another reinforcement. And we just add the material model into that, and it should determine the moment capacity and curvature capacity. And for the service level, we can convert the pre-stressing into axial load, apply with the coupled with the moment, and create a section, and then check the elastic stresses. It's supposed to be uncracked. So we can use the program, even though it's called CSiCOL, for evaluating girders, post-tension, both composite and non-composite. So I think we may have depending upon the time, we may be able to show you that. I can see that there are many questions in the chat, and unfortunately, we may not have time to answer them live here, but we will make sure that we address all of them and send them to you either individually, or we will post them back onto our website later. So kindly keep your questions coming on the chat, and we are watching them, we are following them, and we will try to respond to them. So I think, Shehezard, you can continue.
All right. So for our next section, we'll look at how we can add framing. Okay, so in framing, we are going to consider the slenderness effects on our column. So we simply click slenderness effects from the home menu and then go to the framing option. And from here, we can select any type of framing condition that we want, from fixed to pin and roller. In this case, we will just use the general case so that I can show you the flexibility of how we can select or unselect any column or beam we want along the plane. And then we simply click OK to generate our framing case in the XZ and YZ directions. And you can also view it in 3D to give you an idea of what it will look like. For this case, we can see that our columns sizing needs to be adjusted. So let's do that now. We have our column group. So we will adjust this one to match with our main column. And then let's change our length of the column to be 5 meters. Once this is done, we can click compute to generate our braced and unbraced factors. So the calculations for this are based on the specific code that you have provided. All right. So what the next step is to adjust our loading conditions. So in sway-based frames, we have loading for sway and non-sway. And in this case, it's using the ACI definitions for calculating the sway and non-sway load cases. There is also the option for you to check for your sway. In our case, we will consider the sway and add our additional loading. So here we will set this to be 1000 kilonewtons and then 100 moment top and then 75 moment bottom, and add our storage here to be 10,000. Right. So let's see how this affects our capacity ratio. We can see that the capacity of this column is not able to withstand the loading, additional new loading provided. This is due to the moment magnification that occurs and increases the eccentricity moment. So here we are off by 0.4 from the maximum capacity. To solve this problem, let's go back to our auto design. And in our auto design, first of all, before that, before slenderness, this was the capacity ratio, which is touching within that point. And then with slenderness, it's higher. So for this example, we will simply run with our previous settings for the auto design, and we are able to generate a rebar of 18D40. So let's use that one. Now we can see that our capacity has increased for this column and it's within the limits. And let's check our DC ratio is 0.89. So it's within our 0.9 limit as well. Once this is done, we can also view our detailed reports. So in the detailed report, it will give you all the detailed information, including the key information, the material properties, the section diagram, then the stress strain models used, the rebar configuration, and the framing condition used, including the bracing factors. The next is we can see that our design load has increased. The maximum moment used for design is what will be used for calculating the moment magnification. And this maximum moment will be used for our PM curve as well. Right. We can see finally that our rebar ratio is at 6%, which is within our limits, and everything looks okay. In addition to that, we can see our column summary for more detail. That's it for this demonstration. Thank you so much.
Okay, so once again, thank you so much. I know that we had a lot actually planned. Yeah, we had a lot planned today to present, but as you know, the time is always not enough. And I think it's a good thing because we are now planning more events like this to be conducted and discussing more features, not only of the program, but more problems that we can solve by the same program. And I think we all know that software are just tools. And with the same tools, we can do different tasks, different artisans, different craftsmen. They can use the same tool and create different works of art, which you can say. So it's the same thing for CSiCOL and any other program. They are just tools. So we have to learn how we can effectively use them to solve our complex problems. And we just started few, and there is a lot more we want to share with you. And I just would like to invite everyone to visit, first of all, the website that we will update. But more importantly, we would like your feedback and your comments, and also, your questions, so that we can make sure that we provide the information that will be helpful in your design, in your studies, in your education, and we continue to develop knowledge that will be of value to you. And with that, I would like to thank everyone here, and we will probably allocate more time for the next webinar, hopefully very soon. So thank you, everyone.